Alright, Chem students, today's lesson is going to talk about nuclear fission and fusion. You need to have your atomic structure notes packet, something to write with, and a periodic table. Now, nuclear fission occurs when we bombard uranium or plutonium with neutrons. For example, uranium-235 splits into several different smaller elements and also releases more neutrons and a large quantity of energy. If enough of these isotopes are present, the neutrons will sustain a chain reaction, meaning I have my reactants here, and these are all my products. So long as there are isotopes present, the neutrons from the products will keep causing another reaction. Now, nuclear fission releases huge quantities of energy. Gram for gram, this is at least 1,000,000 times more than energy produced from a normal chemical reaction. Now, because of all this energy being released, we have developed nuclear power plants. We can control the fission reactions with uranium-235. And we have a diagram here of just a basic nuclear power plant. You have the fuel rods creating steam, which is powering the generator, which can create the electricity. So long as we have a cooling tower or some means to cool those rods down, everything can be controlled. The problem is when you lose your ability to cool down the rods. Now, the pros for nuclear power plants are that it's a great alternative to fossil fuels. It does not release greenhouse gases or pollute the environment in other ways. Now, the cons: it's very expensive, and you have to figure out something to do with that radioactive fuel when it's used up. Now, there are three notable disasters when we lost our ability to cool down the reactors. The first one was at 3 Mile Island in Pennsylvania way back in 1979. There was a partial meltdown of the core. The equipment malfunctioned, there was a poor design, and there were some human errors as well. Almost all of the radiation was contained, though. The stuff that was released had negligible effects on the living organisms and the environment around the reactor. It did bring about sweeping changes in design, and it changed how nuclear power plants were operated. Now, Chernobyl happened in Ukraine in 1986. The reactor lid was blown completely off due to a buildup of steam. A massive fire started and debris was released into the atmosphere. This again was a flawed reactor design. The people running the reactor didn't really know what they were doing, and they really didn't worry about safety. A lot of people died due to intense radiation exposure, and a lot of people were harmed in both short-term and the long-term in the environment around there. I think to this day, the wildlife still shows some signs of mutations caused by all that radiation. Our most recent reactor disaster was at Fukushima in Japan, 2011. There were some equipment failures initiated by an earthquake and a resulting tsunami. So nuclear meltdowns, released radioactive materials, health effects, we still don't know about this one. Now, the other thing we use fission for. Fission is great in nuclear reactors, but it was also, we harnessed fission in uncontrolled reactions to use in weapons. The very first one was called the Little Boy bomb in World War II. It used uranium-235, and it was dropped on Hiroshima on August 6, 1945. Fat Man was a bigger version of a nuclear weapon. It utilized plutonium-239. We dropped that one on Nagasaki on August 9, 1945. The destruction was, I think, beyond anybody's expectations, and we haven't really seen bombs like this used since. Now, the other one, nuclear fusion. Fusion involves forcing two relatively small nuclei to combine or fuse into one nucleus. Now, the amount of energy released can be huge due to the mass energy conversion. In fact, nuclear fusion actually liberates 3 to 10 times more energy than fission. Nuclear fusion is what powers the stars, including our sun. In this way, nuclear fusion can be thought of as the source of almost all the energy on the planet, because like we talked about earlier, a lot of our energy conversions start with radiant energy coming from the sun. Now, scientists have not yet found a way to sustain a beneficial nuclear fusion reaction on Earth, The major difficulty is maintaining the extremely high temperatures necessary for fusion to happen, while at the same time containing all of the reactants in fused nuclei. Now, for an example of fusion, we have a star here, and we are going to start with our hydrogen atoms. These hydrogens are going to combine. And then we'll bring them over here. They combine again. And they just keep on combining. Each time they fuse, they are releasing a ton of energy. And they create more hydrogen atoms that can fuse again. Okay, now pause the video for a minute. See if you can determine which one of these reactions is fission, which one is fusion, and which one is just a normal chemical reaction. So for number 1, identify the fission reaction. That would be D. We have uranium-235 and a neutron. This neutron splits it into barium and krypton and releases 3 more neutrons. As for the fusion reaction, B. We have 2 hydrogen atoms fusing to form a helium and another neutron. And then for the chemical reaction, that would be C. We have 2 waters, 2 H2Os, reacting to give us 2 hydrogen and 1 oxygen. Now, the reason this chemical reaction is different from the other 3, we have the same atoms on both sides. We didn't lose any hydrogens, all of the oxygens are accounted for, whereas on the nuclear reactions for fission and fusion, the nuclei actually changed. We didn't end up with the same elements that we started with. Now, let's arrange the following in order from least to most energy released during the reactions. Now, like we said earlier, the weakest one would be a chemical reaction. The next amount of energy released, which is more than a chemical reaction, is fission. And then the absolute most, the one that we are trying to figure out how to master so we can use it for our benefit, would be fusion. Fusion is what powers the stars. Okay, that brings us to half-life. What I want you to do for half-life is cross it out on your notes. We are not going to talk about half-life at all. So cross through half-life on your notes. You are not responsible for half-life. That'll do it for today's lesson, Chem students. So do the corresponding pages in your practice packet, and we'll see you for the next video.